Hello, it looks like most of us are here. So I'm going to give another minute or so, but if you want to get handout number 16, I'm going to stick with the Italians, but I'm going to jump about, I don't know, 300 years or so. So I'll introduce things in a second. Okay. Okay, looks like everybody's here. So we're going to do what we did last class. I'm going to talk about some math, but I'm going to do an abrupt jump that I probably wouldn't do in a normal class. And instead, what I'm going to do is over the weekend, I'm going to post 2 videos. One will be about notation, just sort of like where our current notations came from. And the second will be something about the flow of math to the 1600s. And then where I'll go after that is that next week. And I think it looks like if we're going to do Newton and which I think we should, Newton and Leibniz, any kind of justice, I would like to meet after the break, which I really hoped I wouldn't, but have to do that. But I'll talk more about how that will work. But I'll sort of, I'll introduce some of the material on Tuesday, but Tuesday will be the same, a little bit of math, but lots of times to work on your project. So I'll have more details about that. But this will sort of fill in some of the gaps between Fibonacci and Cardano, who I'm going to talk about today. It's not the cryptocurrency, but so this is about 1200 and this is about 1550. And so there's a big gap. And if you get this handout, there's going to be a way to solve the cubic equation. And so that's kind of that's the theme today. And it's more, it's a little bit more work than the quadratic. And I'll talk a little bit about that when we get there. But this jump of 300 years, at least, just briefly, my understanding of the mathematics in Europe was that as Europe was very isolated during that time period, there were lots of wars, it wasn't so easy to travel from one place to another, that it was very isolated. And it wasn't until the 1500s in Italy and then the 1600s elsewhere that there was some sort of development of a mathematical community in Europe. And I'll talk more about the 1600s next week and after the break. But to me, it's not an accident that Fibonacci brought mathematics to Europe, and that even though it was 300 years later, that one of the biggest sort of advances in mathematics was made. Even though it was 300 years, I think it is significant that the fact that it's in Italy, and Italy was one of the first places to sort of develop, we might think of as high culture, but also, it's where sort of math started in Europe in some senses. And so there always seems to be this theme of algebra in Italy from, during that time. So anyway, so I'm going to go into that. But again, I'm not providing a lot of history, but I think it's important to know this. And the cubic, one of the things to keep in mind is you've seen the cubic pop up in a few places if you've done reading, and we've talked about it, but there's never been, this is the first real solution. And if you think about it, this is like what, over 3,000 years after the Babylonians. So it's a hard problem, and it's considered a milestone of the mathematics to sort of go from the solution of the quadratic to a true solution of a cubic. And there was lots of good numerical solutions, and you might have come across some in your readings in the last week. But anyway, this is the first real solution. So before I begin, any questions about either process in the class or what I've been talking about? And you want to make sure that you have handout 16. It's in the week 12 folder. And there's a lot of information on this. In the front is the outline of the solution. And then the back is just some sort of number 4, I go over the solution in more detail, but just some other things about the cubic equation. So there's a lot of material on this. We're not going to go through the whole thing. I put this stuff on the back, just sort of, there might be a homework follow-up question or something like that. So anyway, so we want to solve the cubic equation, and the version that we're going to solve is of this format. Well, actually, it's going to look like this. And sort of why this is what matters is that on the back I outline it, but you can take a cubic, if you have an equation like this, you can divide out by the a and get rid of that. And so you have an equation that has a leading coefficient of 1. And I'm not going to bother to rewrite it that way. I'm just going to say that without loss of generality, we can assume our equation has 1 for our first coefficient. And that there's a trick where you do a change of variable. And I'm just going to say x is equal to, I'm going to call this, yeah, I'll say x prime, I'll call it u. U is going to be equal to x. I'm not going to go into what that is, but some constant. And you substitute this back in here. And we're calling this u. And then what happens is we're going to end an equation that looks like this. So we can reduce this format of the equation to that where there's no second term. And in fact, if you go through the solution to the cubic, that's what they do. If you were to study this, first thing they would do is they would get rid of this square term, and that's called depressing the cubic. So the idea is that if we can solve a cubic that looks like this, then we can solve any cubic we want. And so that's why we're going to focus on something that looks like this. And probably for things that, for reasons that you've seen already, that the physicality, with the quadratic, I mean, the physicality makes it easier to look at the equation like that. And so fittingly, the way that we're going to derive the solution to this is to actually use a cube. Now that picture is from about 1620. I think that's when the book I found it in was published. And this method and its provenance is really murky, which I'll talk about in a video. It's from about 1550, 1560, depending on how you define it. Somewhere, sorry, mid-1500s is what I meant to write. And we don't know the method, but one speculation, this is one way to sort of derive the method. So and that's what we're going to do today. And there's a lot of algebra, and so just kind of be patient, breathe deep, and I'm going to try to lead you through it in a way that makes sense. I think if I did this in groups in Zoom, I'd be just running back and forth to every group telling you exactly the same thing. And it's kind of like, I think it's kind of cumbersome to go back and forth too often, bring everybody back and then go back in. So I'm just going to encourage you to work on it your alone. I'm going to outline it. So the first thing is look at that cube, and then what you want to do is you want to look at the overall cube. So the big cube minus that little tiny cube that's shaded in the corner, and figure out what that is. And then I'll lead you through that. So if you notice, there's a lot of notation on that, and the side is going to be equal to t. And you can see that if you add the side is broken up into lengths of t minus u and u. And so if you add them together, you get t. So the side is t, and then the side in that little corner is u. So basically, if you see the designation on there, we can break up the cube. So it's like this. We're going to think of the big cube minus the small cube, their smallest. And so that's going to be t cubed minus u cubed. And then that's going to be equal to all the other things. And so the idea is to sort of break that cube up into what's that, 6 parts, one of which we've already used. And think of that, what's left in the cube, if we take out that small corner, is going to be the big cube. That's still not the big cube, but the inside cube. It's the larger cube of that's inside. And then we have the area underneath it. Sorry, I forgot to pin this so I can see this. And make sure I'm not going off the page. And then we have the column. And I'm going to write this on a single line. So we have, and then we have the 2 faces. And you can see that everything has like a formula to it. So if we look at the larger cube in there, this inside cube is going to be t minus u cubed. And then we look at the area under it, and it's going to have 2 sides, t minus u times t minus u, and then that little height is going to be u. And then we have the column above that little u squared, which again is over here, and that column is going to have base u squared, and then its height is going to be t minus u. And then we have the face that's in the front, and the face is on the right as you look at it, and the front of that face is t minus u times t, the height of the entire cube, and then by that length u. So this is the inside cube. This is what's under the cube. This area here is that column that's above the cube we removed. And then these are the faces. Okay. So what we're going to do is it's kind of weird, but we're going to write this in a way that I'm going to tell you in a second. And then from that, we're going to be able to map it to the cubic. So we're going to write this like this.
Would the last one be multiplied by 2 as well?
Yes, I'm sorry. Thank you, Bryce. Yeah, okay. And that's important because there's lots of little algebra in here. Then if you mess up, that's why I say you want to take a deep breath. So here's what we're going to do is we want to write this in this fashion. And I'll tell you why. And then what did I call it here? I call it on the sheet, I call it b times t minus u. And I'm going to switch to another page. So we want to write it this way. So that means we're going to reduce all this so it looks like this. So let's say we've done that, and then I will let you go to work. Let's say we've got it down to this form. And b is really going to be a function of u and t. So it's going to have coefficients there. Once we get it to here, we compare this to 20 equal x cubed plus 6x. And so we're going to say x is t minus u. Then we're going to say 20 equals t cubed minus u cubed. And finally, 6 is going to be what we have for b, which is going to reduce to something really nice. I might as well let you know, it's going to reduce to 3tu when all is said and done. And then what we do is we solve this for t, and then for u, and then that gives us our solution for x. Okay. Now, again, you got to remember that this took a long time for people. People were trying to figure out how to do this. They knew how to do the quadratic, and there was some notation they used for that, which made it easier. But it's also, there was a lot of secrecy around this stuff for, which I'll talk about in the videos. I don't want to get too far afield, but there were duels, there was violence, there was theft, there were banquets, there was betting. all kinds of stuff. It's almost like there was like a cage fight of mathematicians, all about solving equations. So it was like a spectator sport that people bet on. You get mathematicians together. Sounds like fun. And you'd bet on who was going to solve the equation first. And so people would come up with all these funky equations and have a mathematical challenge and see who would win. And people wagered on it. And you can imagine when there's wagering, there's all kinds of other things that go along with wagering. So it was not like the ivory tower. It was a little bit different than that. And I'll talk more about that in one of the videos. So anyway, so the idea is to take this cube, reduce it to this, make this connection, and then solve these. So it's a multi-step process. And I'm gonna have you go to it, but again, I'm gonna copy this over on a fresh piece of paper and work through it, but hopefully you got to this, and going back to this is a good time to look at it, because if you're not sure of this, it's gonna run into trouble. But does this make sense, how I got this equation? And I can go over the little detail. I kind of wanted to give you an overview and then make sure that this made sense to everybody and then set you to work. So if there's questions about how I got a piece of it, let me know and I'll go over those. Okay. Now it seems like bizarre that it's going to work, but let's go through it and see. So here's the equation. I'm gonna actually put it on a fresh piece of paper because I'm gonna work on it so you can check your own work against it. And I'm going to make one more check on it to make sure I didn't make any mistakes. That's the cube. That's the area under the cube. Those are the faces. And that's the column. Okay. Now notice here, the way that I would begin this would be, because this is all you really have to work with, and then I'll let you do the work, is I would factor out a t minus u term and then simplify what's in between the brackets. That's how I'd start. That's how I would start. And so what I'll let you do is start working on it. And again, I wish this were in a classroom because it would be more effective. But I'll let you start working on this. And this is going to reduce to something really simple. There's going to be a lot of cancellations. So the key again is going to be to simplify this. And you can let me know when you get to that point, or if you have questions about how I got there. Okay, are people, are you at that point? Is it okay to go forward?
Yeah.
Okay, yeah, it's not that bad. When you do this on your own, it's a mess. And then, because you're not sure what you're doing. So I tried to simplify it so it wouldn't be so bad. As you can imagine, I usually like to give people less direction, but I just don't think this is the atmosphere for that. Okay. So again, like where did that get us? So the idea is then we're trying to solve, remember, we're going to set this equal 20, x cubed plus x, and then this is going to be we had a 6 there. Okay. Now, before we go any further, does anybody know the solution to this? Did anybody figure it out in their head? It's not that complicated. If you just plug in a code.
2.
Yeah, it's going to be 2. And so it's like, but this will work. It has nothing to do with the fact that it's 2. You know, this will work for any number you put in, and I'll talk about that later. So here's our implicit correspondence. And hopefully that makes sense, where that came from. Okay. So if you have any questions, just let me know. So this is what we're going to focus on. And the idea is to solve for u. Sorry, to solve u in terms of t. And then we're going to plug that in here. And then I'll start you on that. And then we'll go on the solution. So the idea is, like, if you look at this equation, u is going to be equal to 6 over 3t, so 2t. So we plug that in here. And hope that something good comes. This is what I like to refer to as flying blind, is that you kind of have faith that it's all going to work out, even though it kind of looks hopeless. So when you're stuck in an equation that has variables in the bottom, what's your first instinct, or what should be, like your first? It's kind of like an unwritten rule in math. What do you do when you have a fraction? You get rid of it if you can. So if I multiply both sides by t cubed, I get 20t cubed equal t to the 6 minus 8. Okay. So you're probably saying, geez, that, you know, now it's gotten worse, right? We're solving a 3rd degree and now we got to solve a 6th degree, but let's see what we got. So again, you want to move 0 out one side. So we have 0 equals t cubed, t6, I'm sorry, minus 20t cubed minus 8. Okay. Now there's a trick here. I'm going to argue this isn't a 6th degree equation at all. It's something really familiar that's being hidden.
It's a 2nd degree equation.
Yeah. And what's my variable in the 2nd degree equation? It's really going to be t cubed squared minus 20t cubed minus 8 equals 0. So I can use the quadratic, but instead of when I'm going to use the quadratic on, it's going to give me what t cubed is equal to. And notice when I get t cubed, maybe I can just plug it right in here and solve for, I still need 2 to get x, I mean t to get x and u to get x, but I can get u pretty quickly from once I know what t cubed is. So I'll let you figure out what t cubed is as well as what t is. So you should get something like that. I'm going to copy this onto the next page. And I'm going to reduce the 432 just to make life a little bit easier. So I want to factor out anything I can factor out of that. I'm just going to write these over here. X is equal to t minus u. 20 is equal to t cubed minus u cubed. And then 6 is equal to 3tu. So I'm going to reduce this. I'm going to factor out a 4. You know what? I'm going to drop the negative root because we're going to end up getting the same answer if we use the negative root. So I'll just save you some work. 432 is equal to 4 times 108. And for some reason, people didn't factor out. You could factor a 36 out of that too, but they didn't do that. So I'm kind of going by the way that they did it. So this is going to reduce to square root. It's going to be inside 4 times 108 over 2. That's going to be 20 plus 2 square root of 108 over 2. And so that's going to reduce t cubed is going to be 10 plus 2 times the square root of 108. So we'll keep that because that's going to be helpful to solve this. But we need to figure out what t is too. So I'm going to have an expression for that. That's just going to be the cube root of all this. So it's going to be nested roots.
Wouldn't it get rid of the 2 in front of the square root?
It would. Okay. So now I'm going to use this and plug it in here and figure out what u is. So I have 20 is equal to t cubed minus u cubed. I know what u cubed is. I'm sorry, I know what t cubed is. And so I can figure out what u cubed is. I'll let you do that. It should look a lot like this. Okay. And then I'm going to factor out the -1 because it's a cube root and I'm allowed to do it. And it makes this, and I'm sorry, it makes t and u look kind of like conjugates. Okay. Okay, so now we plug these, we know what u is, we know what t is. I'm going to plug it in for x and use that to figure out x. Minus, minus. Okay. Okay, now your next task is to figure out what that is. Well, you suspect that it's 2. But maybe not. Maybe it's a different root than 2. So I'm just going to go to Wolfram alpha. I don't know easy algebraic ways to reduce that. Oops, wrong share. I'm sure I typed something wrong there. Let me figure out what that was.
You forgot the R.
No, I didn't. I typed it wrong. Oh, yeah. I see what you mean. I did. Now, I don't know if you did it this way, but notice that it says it's giving me the principal root. So, but we want the real valued root. And so all that reduces miraculously to 2. Okay, and then if you're curious, on the bottom, I show you a way to kind of show that. I haven't come up with a better way. I'm sure there is. That's what I came up with. I don't know if you've had, I can't remember how many people are in abstract algebra in this class. Is there anybody?
I am.
I have taken it, but I'm not currently taking it.
Okay. Did you do field extensions?
I honestly don't remember.
We did fields, not field extensions.
Because you can take a field of whole numbers and then you can add quantities to it. So you could take a whole number like that and then add a quantity like the square root of 108. And then that's called a field extension. And this creates a new field that has properties. And if you, I don't know, the way that I kind of think of it or thought of it was if I use those properties, I can figure out that this is indeed going to be 2. So anyway, so yeah, it kind of works out weird to be 2. So you know how to solve now you know how to solve a quadratic and you know why you haven't been taught it. It's not as hard as I'm making it out to do. This is the derivation. You can find some pretty simple formulas for it. But I do want to point out that if you wanted to solve, well, let me pause. Any questions about that? You know, it's a non-trivial calculation. And I forget all the details every 2 years. So I do it from scratch to kind of remind myself, and I flounder, and then I kind of, oh yeah, that's what I need to do. But if you don't know the path through this, it can be, you know, you can get lost easily. Okay. So I'm taking that people know. So if we do something like this, notice that we had t cubed minus u cubed equals t minus u cubed plus 3tu t minus u. And let's say I have another equation that's of this form. Let's say I'll just leave it like this. I have d equal x cubed plus cx. Maybe I can just do that and figure out like a general solution. And you can. And it's not crazy. It's, you know, you've got 2 root expressions and they're nested. You know, you're still going to have those nested, you know, square root inside of a cube root, but it's not like insane. So, you know, it's teachable and doable, but we never do. And to find a 4th degree solution, you reduce it to a 3rd degree and solve that. Notice how we used a quadratic to solve this. When you do a 4th degree, you're going to use like an auxiliary equation. It's a cubic to solve the 4th degree equation. And so the thought was people figured the 3rd and 4th degree equations pretty soon after one another. And the thought was that it would work for higher degree equations. But it turned out people proved in the 1800s, like Abel was I think one of the ones, and a guy, I can't remember the other guy's name. I'm just blanking on it. But anyway, it was an Italian. They showed that there's no general formula like this for the 5th degree equation. So it just doesn't work out beyond the 4th degree. And that's something in abstract algebra 2 that often gets studied, is this system of equations. I mean, the solution of higher degree equations. Because it all has these links. And in fact, some of the early solutions of abstract algebra sort of came out of these kinds of issues. Okay, so anyway, so I have a bunch of other questions on there, but one of the questions was to find the other 2 roots. And so we have x cubed plus 6x minus 20 is equal to 0. And we know that x equal 2 is a root. So we can divide this by x2. And I'll do the work for you. And you get x squared. Oh shoot, can't remember what it is. I have it in my notes. I'm pretty sure this is what it is. That you get that. I'm not going to bother to go through that. And this has complex roots. Now, Cardano didn't explore the solutions here, so he didn't discover complex numbers. But one of the things that I mentioned here is this guy Bombelli, and he came right after Raphael Bombelli, and he came in, I think it was around 1575, 1576, I think. And then he worked with this equation, and he discovered imaginary numbers. Like he had negative signs inside the square root. But notice, but they went away when he did his calculations. They just were there for a second and then they left. And so he didn't really make much of it. He just figured, oh, that's fine. You know, they're not going to stick around very long, because he ended up squaring this at some point for reasons I'm not going to get into, because I forget. But so he almost discovered some of these ideas. Okay, so I just wanted to go over this, give you a little bit of the history, just to kind of go over one of the milestones, and also to show you that this is something that you can do, and it leads to an equation that's doable. In the readings, I put a few links up, some that have the history, and there's a YouTube video that I started, and it talks about how ridiculous it is not to teach the cubic equation, and so that has in there, it has like a nice formulation of the solution of the cubic that you can just plug in things. But if you study this sort of in an algebraic context, what you're going to do is it's going to go through that that set of auxiliary equations. They're very, very important. And so for that reason, I think a lot of people leave them in, even though they're not entirely necessary. Okay, so that's all I have for this. And I'll let you look over that at your leisure. And I have some follow-up questions on that. Oh, by the way, remember how I only took the positive square root? Here, you need to get down. I know, unfair. Like right here, I only took the positive root. Can anybody guess what would happen if I did the negative root?
The values of t and u would have just...
Exactly, yeah, that's what happens. So you end up with the same expression for x, except it's going to be in reverse order. You would get x equals this plus this. So so that's why I was able to drop that out. It doesn't give you any additional information. Okay, so any questions or comments?